Hello and welcome to another video. In this one, we're going to be talking about 2's complement, which is the common way that most modern computers store integers in memory. And I'm going to show you how to count in binary on your hand, and hopefully that will help us explain exactly what's going on here. So I'm going to be using my fingers to be counting, and normally you would say, oh, I can only count to 5 on one hand, but I'm going to show you how you can count to 31. Or negative 16, as we'll learn later in 2's complement, just using these 5 digits. And what we're going to do today is we're going to pretend like these digits represent zeros and ones in a binary number. And we're going to count, so this is the least significant digit, so it's left to right for you. It's actually going to be backwards for me, but I'm just going to deal. So you can imagine every finger down, so a series of all zeros, that's going to be essentially 0. And similar to how when you count in base 10, if you ever reach the maximum value, so like if you reach, nine fingers in base 10, and then you were to get a 10th finger, you would overflow to you would carry to the next position in your number. So the 9 would become a 0, and then the next digit would become a 1. The same is true in binary, except our maximum number is 1, so it's a bunch of zeros and ones. So anyway, starting with 0, if we're going to increment that, we will add 1 to the lowest bit, and so that bit is going to become 1. And you can imagine now if we add another bit, you'll notice this is at its latest value, so we will carry that. So that's 2, and again, you can add 1 to get to your least significant bit. And now we have 3, and then 4, and then 5, and then 6, and then 7. And you can imagine like this does a lot of work here. Wait, 1, 3, 7. Yeah, we're at 7 now. So you can kind of imagine like that's how bits are added. So you'll add 1, you have to double, triple carry here. And so now this is 8, and then 9. It's actually really hard to do. 9. There's 9. But yeah, you essentially just carry bits as you go on. Now, what 2's complement is it's a convenient way for computers to store integers in memory. And what 2's complement does is it takes your bits. So let's say we had a 5-bit number, which is nonsense. No one would have a 5-bit number. You would probably have an 8-bit number. But anyway, we're going to pretend that we have a weird system where 5 bits are on a byte. And so this is our unit. And what 2's complement would do was it would use this I guess in your case the rightmost digit, and this will be our sign bit. And so this tells whether it's going to be a negative or a positive number. We're talking about signed integers here. Signed just means that it has, a sign bit. If it's unsigned, you have all of these bits available to do numbers with. And so in the case of counting on one hand, this is actually 31 with 5 ones. I know that because I've counted it out many times. I've actually used this counting trick before. Oh, this is super nerdy. Back when I was training for my marathon, I used to run laps at a local high school, and I can't really count laps with 2 hands. I don't, 10 fingers doesn't quite add up to the right number of laps for a half marathon or a marathon, so I had to count in binary for that. Probably looked like a weirdo running around with my fingers in a contorted mess. But anyway, it helped me remember. But yeah, back to 2's complement. So this bit here is going to be our sign bit, and if we have all of these bits up here, this is going to be 1 plus 3 1 plus 2 plus 4 plus 8, and that'll be 15. So this is our maximum value that we can represent in our 2's complement. So it's always going to be 2 raised to the number of bits minus 1. So 2 to the 5 is, or 2 to the 4, sorry, is 2, 4, 8, 16. And 16 minus 1 is 15. And that's the number, that's what we have here for this number here. 0, 1, 1, 1, 1. And in computers, if you go over the maximum value for your signed value, it's going to do what's called overflow. And when you overflow an integer, in this case, it's going to look like adding 1 to the computer, but to the way that it gets interpreted, it will look like it wraps around to the bottom number. So if you ever worked with something that, you suddenly get negative 2 million and you were just adding numbers, that's because it overflowed. But in our case, let's say we added 1 to 15, and it actually becomes this number, which is 0, 0, 0, 0, 1. And this actually represents negative 16. So this is the minimum value that can be represented in your 2's complement number. And again, as you add numbers, you actually approach 0. So this becomes negative 15, and then negative 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, negative 1. So all ones is negative 1. And this was actually like... This behavior actually surprised me a lot when I was learning 2's complement, because I would think, you know, oh, why isn't it just negative sign bit and then normal 1? And the reason for that is it's much more convenient for computers to represent it this way. So that's why it's done that way. So it makes carry for adding negative numbers the same as carry for adding positive numbers, and so that's why 2's complement is set up that way. But anyway, this is negative 1, not negative, 15. And it actually gives you one more digit that you could count out, because otherwise you would have like negative 0, which makes it makes no sense in 2's complement. There are floating point negative zeros, but not for integers. But anyway, no code for this one, so hopefully this was helpful. If you have additional things you want me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.